Assalamu alaikum to everyone. I would like to welcome you to our lab number 7 for this semester, which of course is going to be the first one we are conducting online. I'm assuming by now you will have installed Java on your personal computers at home, and you will have also installed NetBeans. So with that assumption, the first step is to actually go to our Blackboard course page and download lab number 7. As usual, lab number 7 is a zip file that you're going to download, and therefore you need to first unzip it on a folder on your computer. Once you unzip it, you will find a lab document and also a folder named lab 7. Now inside that lab 7 folder there is actually a NetBeans project. Now for the document, you just double click to open it. I have already opened mine, and it is the document that gives us instruction on what to do to conduct the lab. However, for the NetBeans project, you don't open it by double clicking. You have to actually go to NetBeans and then do File, Open Project to navigate to the folder. If you open, for example, you will see there is a NetBeans project. Just click to open it. I have already opened mine, so I will not open again. Okay, so first let's look at the document. It says lab 7 binary search trees, and as usual we normally state what is our objective. The objectives here is to learn how to implement, this is the keyword, how to implement binary search trees, but also how to use binary search tree. Right, and as usual we have examples and then tasks to do. Now for the examples is basically the Bst class that we have been developing through the lectures. We have explained virtually all the methods of this class, but now we have it as a full class, so we're going to review it one more time just to summarize the content and maybe to explain the remaining methods that are yet to be explained. So this serves as our example, the methods already given to you in the lecture regarding the binary search tree. I will highlight few more examples within the Bst class itself, and then based on that we should be able to do similar methods as specified in the task here. Now as part of the NetBeans project that you will see for lab 7, in addition to the Bst class, we have the usual main class that will test the methods of the Bst class. So there is the test integer Bst, which is just a main class to test the method of the Bst class. You can see here actually in the project, apart from Bst, we have test integer Bst. We have two other classes. LLQ is familiar to you. As you recall, in the implementation of breadth first, we need a queue. So this class is being used as a queue. There's nothing new here, just using the class to help us implement the breadth first. There's also another class called Bst Printer. This is a class that I designed to help us display binary search tree in graphical format, if you like, so that you can understand the process of insertion and traversal, and so on. I will talk more about this one in a moment, but first let us go to the Bst class, have a look at it one more time, review the methods quickly, and explain those that need more explanation, or those that are yet to be explained. As we already explained, within the Bst class we have the Bst node class, and if you recall, the main difference with the DLL node that you are familiar with is that here the generic type T has a restriction. It must be a type that implements the comparable interface. Otherwise, the rest of the code is exactly is very similar to the code for W-linked list. So let's go back to the top of the class just to recap about the methods. Of course, the class itself also, the generic T has the same restriction. It must be comparable. We didn't explain about the implementation of the iterable interface, so we shall explain it briefly now. The class has one variable, the root. We have, in addition to the default constructor, we have actually another constructor that will receive Bst node tree and use it to initialize the tree. We shall see this is needed actually in the Bst Printer class. Okay. We already explained the clear method, the isEmpty method, the visit method. If you recall, the visit method will print the key of the current tree. Okay. We didn't explain this get method. It's simply returning the root. Again, as we shall see, this is specifically used by the Bst Printer, as we shall see. Okay. The search method is exactly as we explain it. Simply going to the left or to the right until we find a node whose key matches our target, and that is the one we should return. Of course, the base case is if the P is null, then the target doesn't exist, we should just return null. I will come back to this briefly in a moment. Now, this we didn't explain is in tree. Now, it's in tree, we don't have to start it from the scratch, because search here will actually return to us the node if it exists, or null if it doesn't. Therefore, if you want to implement a Boolean version of it, just call the search to search the same element and check what is the result. If the result is not null, then we return true. Otherwise, if it is null, we will return false. So there is nothing really to do for this method. Just return the result of the search. Okay. Breadth first is very clear, I think, from the slide. We saw an algorithm, we saw a detailed example. It's very straightforward. All we need is a queue. So this is why we need the other class, the LLQ. We create a queue of Bst nodes and queue the root, and then we start a loop. Okay, the loop involves four things: dequeue the front element, visit that front element that we just dequeued, and then enqueue the left subtree if it is not null, and enqueue the right subtree if it is not null. We shall see how to test these methods in a moment. And then we have the depth first traversal methods, 3 of them: pre-order, in order, first order. Okay, we already also explained the insert method. Very similar to searching, just we keep trying to go to the left or to the right depending on how our new element compare with p.key. Eventually we're going to find an empty node, and all that our method will do is it's going to replace the empty node with a new node containing the element. As you can see, if it is null, just replace p with new node containing the element. But otherwise we keep going to the left or to the right, go to the left or to the right until we find an empty slot. Then we do the insertion simply by creating a leaf node and replacing the null node, which is p, with that new node. Alright, the deletion is also similar. There is a method here that we didn't explain, which is about the height. How to calculate the height of the tree. I have added this method just to give you an additional idea how to implement the tasks that you are asked to do. So I will explain more about this get height when we look at the tasks in a moment. We saw the get minimum method is used to find the successor to help us do the deletion in the case where the delete node has two children. So we have to replace it by a copy of the successor and then delete the successor. I think we already explained this method as well. So the only thing really that we haven't explained in this class is that get height method, which I will come back to, and also the Bst iterator. Yeah, remember, to implement the iterable we must have this iterator method, but to implement the iterator method we need a class that implements iterable. So we are calling that class Bst iterator. Now the Bst iterator here is being implemented very similar to the way we implement breadth first traversal. Let us see how we do it. Of course you have to say implement iterable. Now if you recall how we implemented the same class for DLL, we had a variable temp which we initially set to head, and the next method was simply returning temp.info and moving temp to the next node, whereas the hash next method was simply returning true if temp is not null. Now we're going to do very similar here. The only difference is our tree, our data structure tree here is not linear like doubly linked list. So there are many ways we can go to the next node. Are we going to go to the next node based on depth first traversal? Which of the depth first traversal? Is it pre-order? So if you say next, we got the first one, then the one below it to the left, and so on. Or is it going to be based on in order or based on first order? Or is it going to be based on breadth first traversal? And we have to decide. The next method is supposed to give us the next element, but there are many ways to get the next element depending on what traversal you are following. So in this implementation we have chosen to use the breadth first traversal. So what do? We define a variable p initialized to root. Let me see if I can demonstrate to you what will happen. So let's say we have a tree a very simple tree. Maybe we can use the same tree that we have in the document. In the lab document, we have a tree consisting of 10 to 15. Let's draw it. 10 to 15, 4, 12, and 20. Let me see if I can draw it here. Okay, so we have 10, and to the left of that we have 2, and to the right of that we have 15, and then we have to the right of this one 4, and then this one has 2 subtrees, 12 and 20. Okay, so now what we want is our P initially to be pointing to the root, so that if we say give me next node, the next method will give you 10, and it should automatically move P to the next node. So P will be moved to this one based on breadth first traversal. If you recall, breadth first traversal do it level by level, and within a particular level it will go left, right. Okay, so if we call next again, it will give us 2 and move P to here. Okay, next it will give you 15 and move P to the next level, the first element. Okay, next will give you 4, and it will move to the next one, which is 12, and finally 20. So this is the idea. We want our iterator to traverse the elements and give us in this sequence based on breadth first traversal. So this is how we do it. We initialize P to root, we create a queue, and the constructor here create an empty queue. See here that we didn't really create the queue, we just define it, but the constructor will create it and also enqueue the root, because P is equal to root. So before we call any method, a queue has been created and we have enqueued the root element. Good. So now has next element should return true as long as our queue is not empty. There is something in the queue to be processed, so therefore the method should return true. There are more elements. That's exactly what we are saying here. Return true as long as queue is not empty. Okay. Now what about the next method? The next method is doing exactly what breadth first traversal will do inside the loop. If you remember, it will dequeue the front element and it's going to return the key of that element at the end. But before that, we need to move P to the next element. Okay, so here it depends on if P, because normally we should go to the left first. So here we are saying if P dot left is not null, then Q dot enqueue P dot left, so that the left element will be the next one to be returned to us next time. Okay, and similarly, if P dot right is not null, we enqueue the right. So basically, the next method will dequeue the front element and return the key of that, but before leaving the method, it will move, or it will enqueue the children of that node that has just been returned. So going by our example, the next method will return to us 10, but before leaving the method, it will push 2 and 15 in the queue. So in that way, 2 will be the front element, so that again when we say next, it will dequeue from the queue and give us 2, but also enqueue the only one child of 2, which is 4, as you can see here. Okay, if we say again next element, it will give us 15 and enqueue the children of 15, which are 12 and 20. Alright, next element, it will give us 4, but there is nothing to enqueue. Next element, it will give us 12, nothing to enqueue. Next element, it will give us 20, there is nothing to enqueue. Now if we call at this point has next, it will return false because our queue will have been empty. So this is basically how the method is implemented. I mean both the next and remove. They are going to give us an iterator object that will traverse the list, rather the tree, using the breadth first order method. So basically this is the class. Before I explain the height method and also give you a general idea about how to do the task, let us now test our BST class and see if it is working. So we have the test class, which is the main class. As you can see here, we are creating a BST of integer. As usual, we have option to allow us to select one of the options, and an integer target, which we will use, I think, in the case of searching. Alright. Okay, we created a scanner object, and then in a menu, or rather in a loop, we display the menu to the user, providing an option to check each of the main operations of the BST class. Insert an element, help us check the insert method. Search for an element, help us check the search method. Delete an element, help us check the deletion method. And traversal methods, 4 of them: breadth first, pre-order, in order, and post order. All of these are supposed to allow us to test the different traversals. Finally, we have the get height, and there is a method here to test our iterator whether it is working. I will show you that method in a moment as a static method inside this main class. We have a method called sum, very similar to the sum method we saw in the DLL class. However, this sum method receives a BST of integer called 3. So just to prove to you that the iterator is working, we initialize sum to 0, and we are now saying for each integer n in the tree, add n to our sum. Sum has been initialized to 0 here, exactly as we did it with the DLL. There is no difference because the iterators, the for each, which relies on the iterator, work the same way, whether it is for DLL or for binary search tree. It doesn't matter. So for each element n in the tree, get the n and add it to the sum. So it will be getting the n based on breadth first traversal, as we just explained. So this option here is just trying to test that particular method. Print the sum of the elements. So these are the options. Now we need to handle them within our switch statement. And for the case of insert, we need to ask the user to enter a value, and then we say tree.insert. Okay, just like we used to say list.add, Now the data structure is tree, so tree.insert, and we insert the element that will be entered by the user. Now at this point I need to explain what is happening here, because after inserting we want to display the tree to see how is it, and this is where we need the other class, the Bst Printer. We could have just print the elements of the tree sequentially in a horizontal line, but that doesn't show you how they are actually stored in the tree. We don't know which one is on the left, which one is on the right. So this is the idea of this class. It's supposed to help you print the tree in a tree format, so that you can see which element really is going to the left and which one is going to the right. Okay, now as I explained in a comment here, you are not expected to actually understand this class. You don't have to. Of course you can, if you wish, you can go through the code and see how it works, but it is not required for you to understand how this class works, because it's a little bit complex. So the note here says you do not need to understand the code in this class, you only need to know how to use it. Now how to use it is very easy. It has a constructor which will take a tree of integer. So use this constructor to create a Bst Printer object. Once you do that, that object has one method called print. So just call print and you will see that it will print for you the tree in a tree format. You will see what I mean in a moment. So this is all we need to know about this class, how to use it. And this line in the that option 1 is showing us how in the test integer. So after updating our tree with a new element, we want to display it as a tree. So to do that, you will say new Bst Printer. You will pass to the constructor your tree, so it will give you an object. Now call the .print. So call the print method of that object, and this is all you need to know. This is how to use the class. Okay, new Bst Printer. You give your tree as a parameter. An object will be created. Now call the print method of that object. Good. So after each insertion, we will call this. Similarly, after deletion, as we shall see later, we will call the same tree printer. Okay, let's look at case 2. Case 2 is for a searching. So enter a new element to search. We read the target from the user, and we call tree.search. Tree.search, we give it our target. It's going to return a result. Of course, the result, since our tree is tree of integer, the result will be of type integer. So save it as a variable result of type integer. Now, if we wish, we could have directly print this, but it could be null, and we will want a nice message to be displayed for the user if the result is null. So that's why we are calling the method first, save result in a variable, and now we check if result is not null. We said the element result was found. Otherwise, we print an error message because the result was null. We say sorry, the element was not found. So this is how to test the tree.search method. Okay, what about the next option, which is to delete? Okay, so here we just say tree.delete the target that the user wishes to delete. So we're going to ask the user enter the element to delete, and then we call the tree.delete method. Now if you wish, you can actually save the result, because the if you recall, the delete method is not void. It's going to give you a result. If you wish, you can save the result in a variable and print it, but there is no need. Instead, we're going to print the new tree or the updated tree after the deletion. so that you can see that the new element has really been deleted. So again, to print the updated tree after the deletion, we just call the print method of Bst Printer object. So we have to recreate this object each time we want to print the tree. We say new Bst Printer of tree dot print. Okay. The rest of the methods are all traversal methods, and if you recall, they are void methods. So there is no need for s out. You just say tree.breadth tree.preorder, tree.inorder, and tree.postorder. Now you have to be very careful here, as I normally explain in the lab. The way you call a method depends on whether it is void or not. Some of the methods you're going to be asked to do are not void, so you cannot call them like this. You have to call them as part of the s out or print out statement. Okay. Option 8 is to test our getHeight method. I have not yet explained the getHeight. I will explain it again in a moment. And option 9 is to print the sum, which will be computed using the for each statement, as we already explained. So let us run this example and see how it works. Okay, let me see if I can zoom it a bit. Okay, good. So this is our menu. We're going to test it with the same small tree that we have in the document. If you recall, the elements are 10 to 15, 4, 12, 20. So let us try by inserting these elements one by one. Now if you want the tree to appear like this, you must insert the elements in breadth first order. So first insert 10, then 2, then 15, then 4, then 12, then 20. Because actually the nature of the tree you're going to get depends on the order that you insert the elements. If you insert them in another order, you may get a different tree. Yeah. So let's do that. We're going to say option 1, and our first element is 10. Okay. So 10 has been printed. So far it's only one value, so we don't see it as a tree, we just see 10. Good. Okay, insert again. This time we want to insert 2. Now you can see what I mean. The 2 has been inserted to the left of 10. Why? Because 2 is less than 10, and this is the BST. All the elements on the left must be less than the root. Good. Next is to insert is 15. So 1 and 15. And you can see 15 has been inserted to the right of 10, because 15 is greater. So this is the work of the Bst Printer class, displaying the tree in a graphical way like this for you to really understand what is going on. Next to insert in the next level is 4. So 1 and 4, and you can see 4 is less than 10 but greater than 2, so it goes to the right of 2. Alright, next is 12, I think. Yeah, 12 and 20. So option 1 again, to insert 12, and then to insert 20. Okay, so after each insertion we have a new tree being displayed. This is basically the idea. Good. So far we have been testing only the insert. Let us now try to test the search. Okay, let us search for an element that exists like 12. So option 2, What do you want to insert? What do you want to search? 12. And it is saying here the element 12 was found in the tree. Okay. Let us now try to search for something that doesn't exist. For example, this tree doesn't have 5. So let us search for 5. Option 2. We want 5. And it is saying sorry, the element was not found. Right. Now the rest of the methods, or the next 4 methods, are traversal methods, and we will see. Actually, what I want you to do before you test the traversal methods, according to the lab document, it says here in task 1, for the tree in the above figure, manually find the breadth first, pre-order, in-order, and post-order traversals. This is because actually in a theory exam you are expected to know how to do these traversals. So this is like helping you to know how to do the traversals manually. So I will suggest before you run the code, try to do it manually but on your own, based on the explanation we have in the lecture. As we know, breadth first is the easiest, just level by level. So 10, 2, 15, 4, 12, 20. Pre-order, on the other hand, will always print the key first before doing the left or right. So we're going to have 10 first, then it will go to the left. Then 2, then it will try to go to the left, but there is no left. So now it can do the right, and so on like that. If you have any doubt, go back to the lecture. There is a nice example there showing how to do each of these traversals. So actually I was expecting you to do what we normally do in previous labs, is I allow the student to do this manually before we attempt to do the testing to see the result. So they will compare their manual result with the test run. I think you can still do the same. Take a paper and pencil, see if you can find the traversals, the 4 different traversals of this small tree. Excuse me. Yeah, see if you can find the traversal. And now B says, now run the test integer Bst class using the tree in the above figure and compare the result that you're going to get manually. Yeah, so having done it manually, now you will say, for example, option 4, okay, and you will see that it will list the elements in breadth first order. So now compare this result against your manual traversal. Are you correct or not? And similarly for the in order, or the pre-order, option 5 will print the elements in pre-order. You can see 10 is being printed first because that is the root of the tree, and so on. And 20 is being printed last because it is the last one. Now in order, I forgot to explain this in the lecture. If you notice, in order actually prints the elements in increasing order, sorted in increasing order. So if I say option 6, you will see that the elements are printed in increasing order: 2, 4, 10, 12, 15, and 20. Because if you recall, we delay printing the key until we do the left. We keep going to the left until we find the last left, okay, so which usually will be the smallest element, and then we start going to do the key and then the right. So the elements, if your tree, and this is very important, Shabab, if the tree is BST, then you will have the elements sorted in increasing order if you do in order traversal. I am emphasizing here because if the tree is not a BST, it is just a normal binary tree, then of course the elements will not be sorted. So you have to be very careful if you're in an exam, because you could be given either a binary search tree or a normal binary tree, and you are asked to do the traversals. So don't make the mistake of just printing the element in sorted order, unless you check and are sure that the tree is indeed a BST, not an ordinary binary tree. Alright, so this is the tree, the tree traversals. Next is height. I will explain the height method in a moment, but if you go back to our tree, based on the definition of height, this tree is of height 1, 2, 3. Alright, so if we check for option 8, you will see that it says the same thing. The height of the tree is 3. Okay, finally the sum of the elements. I didn't calculate to see the sum. If you add them up, how much do you get? Okay, that is the last option, option 9. Okay, the answer is 63. You can calculate yourself and see whether the answer is correct. So, but this shows that our iterator method is actually working correctly. Okay. Now let us look at the tasks you are supposed to do, and then I will try to give you a common theme that you must try to follow when you are solving these tasks. So define the following additional methods inside the binary search tree class. First of all, write a Boolean method isLeaf that will take reference to a node of a tree and tell us whether that node is a leaf node or not. Now this is really straightforward. We know a leaf node is the one that has no children. Okay, so all you have to check is that the left and right are both null. But it is also important to check that the tree itself is not null, because if P is null, then it's not leaf, it's an empty tree. So there are 3 conditions to check: that the tree is not null, and that the left is not null, and that the left is null and the right is null. So the tree P is not null, but P dot left and P dot right are both null. If these 3 conditions are met, then the tree is a leaf. So this is a hint I can give you about this one. Now for this method, actually, as you can see here, it is protected. I am not expecting you to test it in the main class. In fact, you're going to need it only in doing this task number 3 and possibly task number 4. But it's not to be tested, so you don't need to have an option to test this class, because here in B, I'm asking you to update the test integer Bst class to have options to test your method. Actually, the note is also here. It's a note. No need to test the isLeaf method. It is needed only in the implementation of leaves count and possibly print null leaves. Okay, so this is the explanation about this one. So the real important 3 methods that you're gonna do are these ones, and for each of them you will also test them in the test integer. So there is need to have options to do that. Okay, let's take them one by one. Get count is similar to the length method in DLL. We want to know how many elements are in the tree. And leaves count, we want to know how many leaves are in the tree. And finally, print non-leaves, we want you to print all the elements in the tree that are not leaf. These are the three important tasks you need to do, and in fact this is the task that I need you to submit. I'm gonna create an assignment for you for this lab in Blackboard, and I expect you to implement these three methods. Of course you need the sleep as a helper method for these two methods as I mentioned. So this has to be submitted, and I'm giving you until midnight of Friday, so that by Saturday, so that by Sunday early morning I should have all the submissions. I'll try to grade them by them. So I'm gonna put a limit for submission for this lab task to be midnight of Saturday midnight. So you have all the weekend. Well, we're already in break anyway, but you have all the days to try and do it. But please, this is very, very important. You must make sure you do them on your own. You have to attempt to do them on your own. If you submit for me, if you submit to me someone else's code, both of you will get 0. You have to try and do it by yourself. Okay. I will give you more hint on this methods after I explain the get height method. The last one here is good to do it also, although I'm not going to grade it. It's saying it's giving you actually a chance to try implementing the comparable interface, which we explained at the beginning of the binary tree lecture. That you should update your student class to make it comparable because otherwise we cannot test our BST with the student class. Right now it is not comparable, so make it comparable and do the comparable based on ID number. Okay, so one student will be less than another if his ID is less, and so on. Once you do that, now you should refactor the test integer to make it test student and test all the methods that we listed above using your student class. Yeah, so this is important to do, although it's not being graded. The main ones being graded are the ones in task 2. Okay. Now let's go back to the BST class, because I need you to be very familiar with the way to implement BST methods. I'm going to delete this one. I hope I can. Yes, good, I can. If you recall, in the lecture I was emphasizing the importance of the recursive definition of BST. Okay, and I said it's going to be very helpful to you when you come to the implementation of BST methods. Now, if you recall the definition, it says a BST is a tree that has one node. So one node, which we call key, and two subtrees. Okay, so you don't think of a tree as having many nodes. It has one node, which we call key, or which contain the key element, and two subtrees, which are left and right. Okay, with this idea, if you keep this idea in mind, you should be able to write any method you are asked to do about tree. Okay, For example, if you recall the traversal method, particularly the depth first traversal, to print all the elements in pre-order, we don't think of the tree as having many elements. The tree actually has only one key. So the algorithm says, if you are doing pre-order, visit the key, then process the left. And this is where the advantage of recursion comes in, because now, since we are defining a method on the whole tree, so the method is applicable to any binary search tree, but our left is also a binary search tree. Therefore, to process the element in the left, we're just gonna make a recursive call on the left and a recursive call on the right. If you remember the code, let's look at it again. The code of the let's say pre-order is doing exactly that. We're gonna take advantage of recursion. So it says, first of all, check if your tree is not null. If it is not, just visit the p. Visit the p, if you remember, will print p.key. Then process the left. Now you don't have to worry at all how to process the left, because you already have a method that can do that. The method you are defining now, just call that method recursively, but instead give it p.left. Alright? And similarly for the right subtree, just call the same method to do p.right. So the recursion takes care of doing the left and right. You don't have to worry about that. You only have to worry about the key. This is very important to bear in mind when you are implementing a binary search tree method. Alright? Similarly, if you look at all the recursive methods, for example, the insert, okay, it says if your p is null, we are ready to insert. Okay, just create a new node and make p to be equal to that. Otherwise, just call the same insert method on p.left to do the insertion, and call the same insert method to do that is depending on whether the element is less or greater. You're gonna call one of this to do the insertion. Okay, so don't try to think of tree as having many nodes that you have to go through one by one until you reach null. No, just call the same method and say, okay, I have realized my element is less than the key. So instead of inserting on the root, just insert on the left. Okay, and to do the insertion on the left, you don't have to do anything. You just allow the recursion to do it for you. So just say insert the element on p.left. On the other hand, if the element is greater, you do the insertion on the right. Okay, similar idea for the delete, and it's the same idea I want to show you here for the get height. Let's go back to our drawing. I want to find the height of this tree. Alright, but the tree has only one key and two subtrees. So how can you formulate the definition for height? The height of this tree will be what? I have only one key and two subtrees. Alright, logically, and remember, if you do a recursive call on the left, you're going to get the height of the left. If you do a recursive call on the right, you're going to get the height of the right. So with these two information, we know the height of the left, we know the height of the right. What will be the height of the overall tree? If you think about it, it's really very easy. It's going to be the height of which of this is the maximum. For example, if this is height 2 and this is height 3, then we're going to take the maximum. We're going to take the maximum of the right, which is 3, plus 1 to get the overall height of the tree. Alright, this is how to think about it. It's a recursive method, and we know we can call the same method to get the height of the left and to get the height of the right. So we know the height of the left, we know the height of the right, we know that there is one key under which left and right are below it. So what is the height of the whole tree? Simply the maximum of these 2 plus 1, and that is exactly what we have here. Okay, get height says if p is null. Of course we must have the base case. I didn't explain this, but it should be obvious. The recursion cannot continue forever. Eventually we will have an empty tree, and an empty tree will have height 0. Okay, but the recursive case is very easy. Get the height of the left and get the height of the right, and find the maximum of the 2. Luckily there is a max.max method. If you recall, you give it any 2 values, it will tell you which of them is the maximum. So you can call it to actually find the maximum of the 2. But notice you have to do the recursive call. Do a recursive call to get height of the left. Do a recursive call to get the height of the right. And then if you wish, you can save them in 2 variables. N1 equal to get height of p dot left, n2 equal to get height of p dot right, and then you say max.max n1 n2. Or if you don't want to call max.max at all, you can use if statement. So if n1 is less than, or rather is greater than n2, return 1 plus n1, otherwise return 1 plus n2, and so on. Okay, so but this is just one line. Just say 1 taking care of the key plus whichever height is bigger between the height of the left and the height of the right. So really very easy. The other point note is that for each of these methods there is usually a need for an auxiliary method. So here we will call this one, but we need to give root as the initial value of p. Okay, so I delayed this just to give you more hint how to do the task you are asked to do. So let's go back to the tasks. This one says write a method get count that will return the count of the nodes in the tree. So again, don't think of the tree as having many nodes that you will have to all count. You are thinking in loop way or iterative way if you do that. No, your tree is like this. It has a key, it has left, and it has right. You can call get count of left, and automatically you will know how many elements are in the left subtree just by making a recursive call. You can call the same method get count, give it your right subtree, and it will tell you how many elements are here. So we know how many elements are in the left, we know how many elements are in the right. The question is how many elements are in the whole tree. I think it's obvious to you what to do. Really very easy if you think of it recursively. Imagine how you will have to do this if you have to do it using loop. This is why I kept emphasizing the recursion makes the job much easier. It makes the code simpler. Of course there is a cost in terms of speed and memory, but it simplifies the code. So this is what you have to do regarding get count. I hope I have given you enough hint to do that. The next method is leaves count. So here we are interested in finding the leaves, not all the keys, just the leaves. So really it's very similar to get count. The only thing here, we need to make sure a node is not is a leaf before we count it. Here we are counting all the nodes, but here we need to count only the leaves. So again, if we go back to our diagram, it's really very easy. If you think of your tree like this, and you know that you can call the method to find the leaves in the left, and you can call the method on the right subtree to find the leaves in the right. Okay, the question is, how many leaves are there in the whole tree? Obviously we don't count key, because we don't count this node that has the key, because it is not a leaf, it has a subtree. If it has subtree, we don't count it, it's not a leaf. Simply the leaves in the left plus the leaves in the right. This gives you the recursive version, but now you have to think about the base case. Actually, there are two base cases in this case. First of all, the tree could be empty. So if it is empty, we just return 0, because it has no node at all, not to talk about leaves. Okay, and then there is another case where the node itself is leaf. So the left is null and the right is null. In fact, that is why you need to call the first method that you did there, the isLeaf method. So you can use the isLeaf to check, first of all, if your P is leaf. In that case, just return 1, because we know this is a leaf, just return 1. Okay, so there are 3 cases. P is null, P is a leaf, and then P is not a leaf. If P is not a leaf, this is where you need to do the recursion to find the number of leaves in the tree. Yeah, so this is the hint how to do this one. And the last one is about print non-leaves. So here we want to print all the nodes that are not leaf. So again, this really is very straightforward, because we already have method that can print all the elements. The traversal method, they print all the elements. For example, if you take the in order, it will print all the elements. Okay, how is it printing all the elements? As we already explained, it prints the elements in the left, then it prints the key, then it prints the element in the right. Now printing the element on the left and right are just by making a recursive call. So now all you have to make sure is when you are printing this key, because actually it is printing the key that is important. In the one that is printing everything, we always print the key. Alright, but now we need to be sure, is the key a non-leaf before we print it. This is the only difference. Okay, in the in order, for example, assuming you want to print the elements that are not leaf in order, then you just need to modify the in order. In order was printing all the elements, but now we want to print only the non-leaves. And if you look at your method, the only statement there that is doing the printing is the visit method. If you look at the BST, the in order, yeah, this is the in order that will print everything. And the only statement here that is doing the printing is this visit, print the P. So now all we have to be sure is that before we print the P, check that it is not a leaf. Alright, that is the only thing you have to do to make sure it prints only the non-leaves. I hope this gives you the hint how to do the tasks. And this brings us to the end of the explanation for lab number 7. As I said, I'm going to put an assignment on the blackboard for you to do this assignment, to do this lab as an assignment, and submit it by midnight on Saturday, so that I get it by early morning Sunday and try to grade it for you. Thank you very much.